Good afternoon, everyone. Hope you're having a great day here. We're starting our technology track here right now. We're going to start off with a talk from Frederick and Abhisek Balasubramanian, who've come from India to talk about some new ideas for our Mars rover. Gentlemen?
Good afternoon, everyone. My name is Alan, and that's Abhisek, and we're from Hindustan University from India, Chennai. And we've developed a concept of an Arachnid six-wheeled all-terrain explorer with a 7D of robotic arm. It's not working.
None of the buttons work right. How about the laser top button?
Yeah, that
That works. That should be good enough. I'll get one of the AV people.
Sure. For abstract, and these are the key points that we mentioned, that the first thing that's going to be inspired by Arachnid, and it has an adaptive dynamic system which uses a steward platform for balancing the body, has 6 DOF, and a robotic arm with 7 degrees of freedom, and A-star with fuzzy logic implemented for the navigation. And we also have the main purpose of a rover is to go and explore planets, detect the presence of life, and carry out experiments. And so we proposed a few methods in which we can detect the presence of sugars, amino acids, and lipids, the basic constituents of life. Okay, so why an arachnid? So the arachnid, basically, it's similar to a spider. Yes, they do have 8 legs, but we've decided to go with 6. First thing with respect to steering of the rover. And second thing, that we have a proposal that the front, we have 2 extra hydraulic systems that can be used as forklifts for gaining stability while the rover is performing operations such as digging. And so the multi-segmented legs also provide stability and while traversing over rough terrain. And dimensions of the entire rover dependent on Martian topography and vehicle dynamics. And this is common across in amphibians or in sea creatures and land. So this is an image of our suspension system. So again, this is similar to an arachnid. So it has a hinge joint over here, and we have a coilover spring, and this has a push rod suspension system and a normal coilover spring over here. So basically, go to the next one. When we have displacement along the y direction, we have a compression along this coilover spring, and this has hinge joint over here, and this is actuated by a push rod, which translates the resultant force into this coilover spring. So what is the adaptive dynamic control? So the reason why we came up with this was because we wanted to control in which direction the body was aligned with reference to the suspension system. So typically, NASA uses a rocker bogie suspension system, but we're not able to control the CG of the rover to that great of an extent. So this is a 6D of hexapod hydraulic lift system. So we've separated basically the rover into 2 subsystems, the suspension module and the chassis module. And we have 2 modes in which we can control this. So you can go to the next one. So the first one, this is the image of the hexapod system. So this is our suspension system on which the suspension legs are mounted, and this is where the chassis frame where the chassis is mounted. So these hydraulic lifts, they orient the body with respect to the suspension in two different ways. Next. So the first one is the mirror mode. This is essential when you're going downhill or climbing uphill. So what this basically does is the chassis basically reflects the negative angle of the suspension frame. The other one is a level mode. When it's traveling over normal terrain, the chassis is always kept parallel to the ground, regardless of what orientation the suspension frame is at. So the wheel. So what we wanted to do was we wanted to go back and design the wheel from scratch, and especially considering the problems that NASA has faced in their aluminum wheel frames. So the first thing that we did was we divided this into multiple segments, because NASA, what they had experienced was tear and holes forming in the wheels. So we split it up in different segments. So each member of each element of these wheels behaves as a cantilever. So when it traverses over any particular obstacle, each element goes under a cantilever deflection. So it has also a camber of 3.5 degrees, and I'll show you why. Next one. Okay, next. So when it traverses over an obstacle, we have this inclination of 3.5 degrees, so that when it traverses over an obstacle, the surface area contact with the ground is actually increased. So the 7D of robotic arm. So what we've done is taking a typical 6D of robotic arm, we've added a linear motion with the help of a linear actuator, and the gear drives are planetary harmonic and direct drives, similar to a conventional robotic arm. And this is the image of that. So this is basically what we've added over here. So considering the height and the dimensions of the rover, we can use this linear actuator for other purposes such as drilling.
So the electronics is kept in a closed box where it can be operated in normal temperature, even though the temperature of Mars is affecting the electronics inside it. And the onboard computer, which is used for processing all the data and controlling the rover, is capable of doing parallel processing and is equal to a laptop computer. So this is the artificial neural networks which the processing system uses, and this artificial neural network is developed based on various positional data taken from the rover and the robotic arm, which is fed as the input. And these input are simulated, and the simulation was carried out on Adams, and the data was collected, and it was fed into the ANN, and output was generated. Okay, so the other form of feedback system we use is vision system. So the vision system plays the major role in navigating the rover on the planet Mars. So there are two cameras on the rover. One is the belly camera, and other one is the stereo vision camera. These two cameras collect real-time data from the actual atmosphere, and these data which are collected are matched with the actual location, and it is inputted. The image is processed, and the processed image is used for data acquisition, and the data acquired is fed into the microprocessor, which in turn processes the data and gives the commands to microcontroller, and this microcontroller in turn drives the drive system, from which the feedback is taken and fed into the microprocessor for other corrections. So this is how the image processing is done using MATLAB tool.
So coming to the soil analysis capabilities of the rover. So the first thing that we've decided was that we'll go for detection of amino acids, sugars, and lipids, and I'll be following up with the justification of that. And the method that we propose is introduction of bacterial strains to behave as biological sensors and detection of the occurrence of ice nucleation. So these are two types of bacterial strains that when we inject them into the soil sample, you have ice nucleation activity demonstrated. So that could indicate the presence of amino acids and sugars. So why did we go for these three elements? So first thing is that lipids have high resistance to degradation by enzymes when a microorganism dies. So we could actually use that, and so these actually last longer in the soil samples, and that could actually be used as a reference for testing. And amino acids and their importance in our biological processes are considered to be fundamental to the indication of life, which is why we also went for that. And the presence of sugars in the form of glucose or sugars, sucrose or fructose, also indicates the presence of respiration and energy production. Next. And so a scientific equipment that we found from another paper was that near-infrared spectroscopy could be used and uses very small soil samples to carry out the necessary observations. So this is the final model of our rover with all the Arachnid suspension system, our novel wheel, and the robotic arm. And just for a fun fact, that rear wing was introduced so that in the case of Martian storms, that we could generate enough downforce to keep the rover in a high enough traction on the ground. Thank you.
Just stay up for questions.
Yeah.
I'll just take questions. You can keep that. Well, thank you, gentlemen. I'd like to open the floor to questions now from anyone.
Do you have any idea of the power consumption on using the active stability with hydraulics?
See, we've not gone deep into the power system because of different technologies used, so we've not actually gone into it.
I also did a little bit of research with hexapods, and they were non-wheel, and so they were just doing gates. And we noticed that when going up an incline, by using different gates, you actually have less chance of slipping on an incline. And it was pretty interesting that you can kind of depending on the angle of the body itself, that it would reduce a slippage. How would you think about changing the gates, like the way each individual legs move to kind of compensate for that?
See, the thing is that completely depends on the positions of each individual hydraulic actuator. See, this thing had a certain ratio of the body length and the width. So depending upon that, we place our actuators. So that we have to derive the mathematical relationship between each one. And so once we get that, we know where the CG will be. And if the CG falls out of the body, we'll know whether we can gain the required traction. Sure. Yes?
Another question about the wheels. If each of the, I'll call them paddles for lack of a better word, has space between that and its neighbors, what about the business of sharp rocks or projecting between the panels and stopping the wheels from moving altogether? Or a length, let's say that it encounters a length of shale, or I've seen pictures on Mars, there's chunks of shale. And long enough, it would project right through and block the wheels from turning.
Right. So we do have a navigation system that tries to avoid such situations from happening.
So if at all it happens, we have an hydraulic system which can lift the wheel up. So we spoke about it in the beginning itself, which will be able to lift it up, the forklift, so that the wheel can come out of the rock.
So the individual wheels can be lifted up then, or is it a whole side?
The whole side. One side will be lifted so that it can come out.
Any other questions? Going once, twice? Okay, well, thank you. We now have a 10-minute break before the next presentation. Thank you again, gentlemen.